Okay, so Anshul, now you can carry on. You can share the screen first. Yeah, yeah, perfect. Yes. Okay, carry on, Anshul. Yes, I'm just switching. Hello, Anshul, are you audible to everyone?
Sorry for that. I have changed my headphones. That's why. Now I am
Yeah,
audible to everyone. So just like in the Cadence, we are using that remote desktop connection. Here also we have to use this remote desktop connection. Go for that 241. Don't go for that 244. You will face some problem there. So just go with this. So that's your desktop and remotes. That now here you have to create one folder. I have already created one folder, that Anshul one. You have to create your own folder. You can give any name for that folder. In this folder, just right click and open in a terminal. Now in that Cadence, we used to write this virtuoso. In this we will write SDE space shift end. So for this demonstration, this will be divided in three parts. This demonstration which I am giving is divided basically in three parts. In first part, we'll construct the device. In first part, we'll construct the device. In second, we'll run that device by giving voltage. In third, we'll plot the graph between current and voltage. So for constructing the device, we should this open this window. So basically we are going for that PN junction. So PN junction has basically two parts, two regions, P regions and N regions. In for a basic PN junction device, we should have that two devices. Material should be silicon. You can take any material for that. In two regions you should apply doping, and then you should give that context. So first I'll go for that designing. So first of all, for that you should go in that view. In this view, in GUI mode, you should select 2D mode. Since we are designing our circuit in two dimensional, so you should select that 2D mode. After that, just go on to draw and select this auto region naming. If you select this auto region naming, it will automatically name your region any name. So just deselect it, so you can give the name by yourself. So after that, again go to draw. In this, you select this exact coordinates. This is one shortcut also for that, so you can choose from anywhere you want. After that, since we are going for the PN junction shape is rectangular one, so we'll go for this rectangular shape and we'll draw. Now they are asking for the coordinates. What are the coordinates for your device? So your starting coordinate should be, x coordinate should be 0, y coordinate should be 0. In x direction, our length should be 90 nanometers, so we'll set it 0.09, and here it's 30 nanometer, so 0.030. Press OK. Now this is what you want to give your region name. Since we are designing first n region, so I am giving this region n. You can give any name, whatever you want. Since we are designing for first n region, so I have given the name n region. Okay. Now in what coordinates you have to design this you can select from here. There are three coordinates: y, x coordinate, xy coordinate, and x and minus y coordinate. I'll go for that x and minus y coordinate. Now this is basic structure which we have got. So we'll break this into small grids. For that you have to select this grid option. So you can give the grid width whatever you want and grid height whatever you want. It should be, you can give 2 nanometers, you give 3 nanometers, 4 nanometers. I'll go for 3 nanometers. Apply and show. Now this, our device has been formed in a grid part. Since now this is the complete n region and our PN junction have two regions, P region and N region. Now we'll go for that P region. For that you have to select this snap to grid option from your window, and with this rectangular you can now, since the total length of our device is 90 nanometers, so for we will make our PN junction P device just half. So here it's showing 0.048 nanometers, so we'll make it 45. Okay. Now again, since this is region 2 is our P region, so we'll give whatever name you want to give, you can give. I'll give it region P. Okay. Now your device has been divided in two regions. This is your P region and this is your N region. After that, this is pure silicon. This is basically pure silicon. One thing I have to forget you to tell you that you can select any of material which you want from this drop down list. So since we are doing pure silicon, it's on, we'll select only silicon. Now the next part is regarding doping. We have to dope our P region and N region. So for doping, we'll go in this device, constant profile placement. So since we have divided our device in two regions, P region and N region, so from here we can select the regions. When there is N region, this will be selected, and when there is P region, this region will be selected. So first we'll go for doping for N region. So we'll select N region. Here you can give the name N. Also here you can change the name N. Now since N region, you have to dope with phosphorus. So in this you'll select phosphorus. Regarding concentration, the maximum you can go for 20 e to the power 20, from e to the power 16 to 10 to the power 20. So I'll go for 20 e to the power 20. So 1 e to 0. After add placement, now this region has been added with the phosphorus impurity. Now again we have to dope P region. So we'll go for P region, select P region. In this we can dope with boron, so we'll select boron. Now in this region, concentration you can vary by yourself. You want to give it 20 e to the power 20, you can give it e to the power 20, you can vary. I am going for 19. Again here also I have to change P at placement. Now if you want to check that whether you are done correct or not, just go here in N region. The doping concentration is 1E20, and in P region it's 19. You can close it. Now the third part, the major part, is to add the contacts. For adding contacts, you have to set contact first. After setting the contacts, you can apply them. So for that, you should go for contacts. In this contact sets, so since this is P region and this is N region, so first I will set the contact. So P underscore, you can give any name to your contact. I am giving that P underscore contact. Whatever name you can want to give, you can give to your contact. Then set your contact. Again, second contact is N contact, and set. These two contacts you have set. Now you can change the color also. For for N contact, this is RGV. So 1 and 0. For P contact, it's 100. Again, since you give your contacts at the edge of your device, so here in this icon, you should go for select edge. Now using this arrow, you can select the edge and activate your contact. So first this is your N region and this is your P region. I will again go to contacts, contact set, select P N contact, activate, and place my cursor here. Now go to contacts, set contact. Now this my P contact has been set. Similarly, again I'll click to this edge, go on contacts, contact set, activate my P contact, activate, contacts, set contact. Now, since our contacts are set, now we'll go for meshing our device. For meshing our device, we'll go on this mesh option, defines mesh window. So since we have to select our device is in rectangular in shape, so we'll go for this defined reference window. We'll go for this rectangular shape and select our device. Make this a little bit more than our device. So this will select our device. Now again, we'll go to the mesh. We'll set our refined placement. So since only one device is there, only one window is there, I'll select this. My maximum element size, I have to give that refined placement. So my maximum size will be 0.003. In y direction, it will be 0.003. And my minimum size is 1e minus 6. Again here also 1 e minus 6. Create refinement. Now refinement has been created. At last, again go to this mesh option and build mesh. So here click on build mesh. Now this our device ST model, mesh model has been created. You can see this here, that you have given doping concentration 1 e to the power minus 19 this side and 1 e to the power plus 20 this side. So this is basic structure in SD model. Again, this will give you the basic that what grid we have selected in this mesh. So this is our basic device structure. Up to that, we have just constructed our device and created a mesh. For I will just repeat all the steps what we have done in short. First, we have created our device. Our device, first we have generated ends, a complete end region. The length of device was 9 to 90 nanometers, and the width was we have taken with 30 nanometers. We have applied the grid of 0.03 nanometers. Then we have created P side at one side. Since the length of our device was 90 nanometers, so the P side we have created that's 45 nanometers. After that, we have added impurities to our N side and P side. In N side, we have added e to the power 20, and in NP side, we have added e to the power 19. Again, I am saying that you can vary these values as you want. You can vary these values. So after adding that, we have generated contacts. For contacts, we have given two contacts, P contacts and N contacts. You can vary the color also for the contacts. After that creation of contacts, we have built the mesh. There we have set the refinement values. Maximum value we have set to 0.0, that is 3 nanometers, and minimum values 1 e to the power minus 6 nanometers. Now this first part we have done. Now we'll go for running this. So for running this, there is one CMD file which contains all the properties of this device. I'll show you that CMD file. This is CMD file. In this file, we have that grid which we have created plot. This plot will whatever will be plotting the graph, this current output parameters. So we'll run this file. So for this, we'll go for, again on our window. We'll write S device space diode shift underscore DC dot CMD. This is what we have constructed. The program is running. So after the complete running, you can see this initially. In after all, I will show you that CMD file. Initially, we have given that P and N voltage both on P side and N side. We have given the voltage 0 volt, and after that, we'll go on gradually increasing the voltage from P side from 0 to 1 volt. And what are the changes in the current? This will see in the graph. So this basically is performing that part in the form of coding, that whenever the voltage is increasing from 0, then 0.1, 0.2, what are the changes in current? This basically CMD file has performed that experiment. Now after that, running of the CMD file or run our experiment has finished. Now we'll go for just plotting this graph. So again, as will type as usual, and this Centros window will again open. From here, we have to select the IV characteristics file. Where after all that graph, I will show you that CMD file. In that CMD file, this special IV function has been created for plotting the graph between current and voltage. And for this, it should be, I have created this IV new diode TOS DS. My file name was new diode. So this is the standard file which we has created, command which is there in CMD file. My file name is new diode, and dot design dot plot. This file you have to select for plotting your graph. Whenever you construct your device and run that CMR code, this file will be generated in your that folder you have created. So you have to select. In this is IV already generated command in your CMR CMD file. This is the name of your file which we have created, underscore des design dot plt for plot. So if you, for example, if you have given your name diode only, so this will be iv underscore diode underscore des dot plt. If you are given d1 name, then iv underscore d1 underscore des dot plt. I'll select this file, open. Now what respect we are plotting our graph, we have to select. So we are giving the voltage from 0 to 1, we are varying the voltage in P side. So we'll select P side and outer voltage. What we are giving, outer voltage is varying from 0 to maximum 1 volt. That I will show you in that CMD file, that our starting voltage for P side is 0 volt, and we are gradually increasing that voltage from 0 to 1 volt. So it will plot on x-axis. Again, total current, what is the total current we have got, that we will plot on y-axis. So this is our graph, how our voltage is increasing, and with respect to that voltage, how our current is increasing. So this is just a demonstration how to plot a graph between outer voltage and total current. So this is simple and demonstration. You can, where you can play with this, you can change the various values and increase the current value. If you want to increase the current value, the three things you can change. First, I go to that device structure. In this device structure, if you change, if you decrease the length of device, if you increase this length of device, your current will be increased. Secondly, you can increase the width of your device. If you increase the width of your device, again you can increase your current. And third, in that CMD file, you can we are working in standard 300 Kelvin temperature. So there is no effect for temperature. You can increase that temperature, and then you can see what are the variations in current in your this graph. So this is your kind of assignment, or assignment. You can change that values, you can change the width, you can change the length, and by that you can see that the current is great. You can increase the value of current. Again, this is the graph. Now if you want to import these values, because in that CMD file we have given the difference of 50 time intervals between that 0 and 1 volt. So we'll get 50 different values for current for different 50 values of voltage. So for that, you can go to this data, export. Since there is only one curve, so you select this curve, export. You can give any name. I have already created one graph, 1 2 3. You can give any name, 1 2 3, and save. So 1 2 3, save. So Here you can see that this voltage is varying from 0, 0.02, 0.04, 0.06 up to that we have got all the values. So this is just for a single temperature, single width, single length. Now you can vary the length by yourself and see what are the different graphs for the current you are getting. Similarly, you can go for varying the width. When you will vary the width, you will see that how the current is increasing. Similarly, in that CMD file, you can vary the temperature from 300 Kelvin to 600 Kelvin. Also, you can go for higher values of temperature, and you can see the variations there also.
Okay, thank you. Anshul, can you please open the S visual plot once? It's already open. Left, left, left one, left, left. Yes. Okay. So all of you can see that the currents which he has shown over here is essentially leading up to like the variation is from 0 to 1 volt on the x-axis, and on the y-axis we find that it is reaching up to how much, like 6 milliamps or so. Okay. Now the first assignment which I will be sharing with you today itself, the first assignment will be to investigate how this IV characteristics will change as you are modifying the device structure, the device doping, as well as the temperature. Okay. So if all of you are already aware of one thing, like Anshul, can you show me the Centaurus structure once? Here on the left. Yeah, left. Yes, this one. Yes. So all of you are aware that in the BTEC itself, we have seen that if we want to improve the performance or the efficiency of a BJT, what do? We need to ensure that the recombination area of the diode should be as low as possible. Okay. So we are just about to start diode in our theory classes. So this will become much more clearer from the mathematical precision also. But as of now, you can understand intuitively what is happening is that you can clearly see the junction between the P and N region in the middle, right? So the thing is that the depletion region is very, very close to that junction, and the rest of the entire P and N regions are full of neutral region. So neutral means they are essentially having the ionized impurities as well as the free carriers. So essentially in the P type, you are going to have the holes as the majority carriers, and the N type region, you are going to have more number of electrons. So as a consequence, whenever the minority carriers are crossing over the depletion region and going to the N region, for example, so that means the holes are coming from the P region and entering into the N region. What does it find? It will essentially find a stream of electrons, free electrons over there. So what happens? Those holes will recombine, correct? So as a consequence, if you are keeping this neutral N region as well as a neutral P region wider, you are essentially losing the free carriers because of recombination. So the first strategy as an engineer to improve the current of the diode will be to reduce this neutral region. Understood, everybody? All right. Second, what you can do to improve the currents and all, what you can do is you can make the device wider. Why does it matter? Because remember, a diode, BJT, these are all bulk devices, unlike the case of the MOSFET. Remember, this is one of the reasons why MOSFET is scalable, whereas BJT and diodes are not scalable. What is the meaning of the scalable devices? You can scale the MOSFET, right? Why? The reason is that if you scale the MOSFET, the performance improves in the case of the MOSFET. On the other hand, if you scale the BJT or the diode, the performance depreciates. It becomes worse. Okay. So what, as a part of this exercise, as a part of this assignment, what you have to do is, here the target is to improve the currents. So I have not specifically mentioned anything about which way. So what I'm suggesting is you can make this device wider. Okay, so the thickness of the diode can be increased. All right. So the first way to improve the current will be to reduce the neutral region, N region and P region, neutral region, you have to reduce. Second thing will be make the diode wider. Third region will be operate at a higher temperature, as Anshul has rightly pointed out. With higher temperature, what happens? Number of carriers will increase. Okay, that is also something which we have studied in the class, and also we will study even more. So you can increase the temperature. Okay, what else? How can you increase the currents even further? If you can create higher amount of field at the junction, how can you do that? If you can essentially have the N doping and the P doping higher. So what is the doping Anshul has taken? As I discussed today in the class, what is the maximum doping you can go? It will be around 10 power 20 or 10 power 21 on either side, right? So you can test that as well. Okay. So there are several such strategies, and what I want you to do is ensure that all of you should do it as an assignment and figure out the IV characteristics for multiple values of the parameter which you are changing. For example, you can change the width of the device. So when you are changing the width of the device, so you should have multiple curves. You have to plot multiple curves corresponding to each of the different device widths as whatever you have taken as the legend of the curve of the plot of the figure. Okay, so that will be your deliverable as the part of the assignment report. Okay, so in this process you are going to learn this tool, and in the next class we are going to look into MOS capacitor, or let us say we will see what we can do. But our target over here, as we have seen today in our lecture, is that it is only taking care of the DC characterization, that is IV. Later on in the subsequent assignments, we are going to check for the CV measurements for the AC analysis. Okay, so I want you to start working on this synopsys tool. And here, as Anshul has showed you, and that is very important, is that how to export the figures data into CSV files. Because later on in this course, when we will be doing machine learning, or let us say how to use this device specifically for making circuits in Cadence, in that case, we need to have access to the data or the simulation data which is generated by Synopsys. Okay, so make sure that you have obtained the CSV file, and you can use MATLAB or Python or something for plotting those figures as well. Okay, all right, so that's all for today. So the assignment will be due until this weekend. Okay, Saturday or Sunday, you take time until that. So this video is getting recorded. So as I said, I am going to upload this on YouTube, and I will share with you the entire video so that you can pause it and essentially learn the tool very nicely. Okay. So thank you, Anshul. So
Sir,
I'll just
one. I
yeah.
want to describe this CMD file.
Yeah. Please do that. Yeah.
This is the basic CMD file, which already had been created by the sir for this PN junction. For every circuit, there is that CMD file. So basically, here my the circuit's name was new diode. So I have given the name new diode. So whenever you get this CMD file, you can take it from me or sir. You have to give the whatever the device name you have given. You have to give the name here. Again, we have taken two contacts, P contact and N contact. I have given the name P contact and N contact. If you are changing the name, you have to change the name here also. Our starting voltage was 0 volt at the P side, and N side our starting voltage was 0 volt. Again, this I have already told you that this IV characteristic is our main graph that we have plotted between current and voltage. So better, we have seen that after this, whatever the name of your circuit is there, that my circuit name is new diode dot des dot plt was our graph. So better you should know all these points. Thanks, sir.
Hello.
Hello. Okay, sir.
Yeah. Am I audible?
Yes, sir.
Just a second. Yes. So all these specifics about the CMD file will become clear as you start using them. So what I will do is I'm going to post this diode underscore dc.cmd on our Google Classroom. Okay. So that all of you can download it, because this is the beginning, the first assignment, simulation assignment. So I want you to download this and work it out on your own. So as you go ahead with more complicated devices, essentially, you are going to learn more and more about this CMD file or the command file. Okay. In case you are curious to know, this language which we have used over here is usually called tickle or TCL script. So TCL script happens to be one of the most ubiquitous uh, scripting language in the industry today. Okay, so we will learn more about TCL scripting later on. Okay, so as of now, you just take the CMD file and you have to tweak these values so that you can get the results on the diode as you want. Okay, all right, so that's all for today. The assignment for this is due on Saturday or Sunday, let us say. I'll give the time until Sunday itself, since it is the first time. Okay. Thank you so much, Anshul, for joining. And I want all of you to work on this, because this happens to be one of the main workhorse, and this is the industry level, industry standard tool for designing the devices uh, at a professional level. So essentially, I can share with you that even Texas Instruments, Intel, AMD, they are actually using this Synopsys TCAD for the device level work, and they are using Cadence for the circuit level work. So I want all of you to have hands-on experience on this, because this is the industry standard. Okay, that's all for today. Thank you so much for joining.